All right. I think we are live. We are live. Excellent. Okay, guys. I am going to trust that we are live. And since we are live now, just give me 1 second. Hey, Iris? Iris?
Yeah?
Could you check again?
1 second.
Yeah. It should work now. Oh. Leslie, can you check on YouTube? Check if I'm live on YouTube. Iris isn't reliable. 8th floor math. 8th floor math. Yeah, 8th floor math. Just type it in.
You're live.
I'm live. Thank you. Thank you, Iris. Sorry about that. I had to deal with stuff. Okay, whatever. All right. I had to deal with stuff. I had to make sure this was working. Okay, so we're going to, for the first time, at least for me, we're going to prove the volume of a sphere based off its radius. Okay. At different points, I've known what the volume of a sphere is. I think I've used it before in like school. I forget though. I think it's like I remember there's a fraction. The radius is cubed, I believe. Yes. I mean, it's going to be cubed. And then this is volume. And then there's pi as well. And that makes sense. But I don't quite remember. And I haven't done this proof before. This is the first time I've done this, and I thought it'd be a very cool idea to do it live. That way you guys could see the process of how I go about making a proof, a mathematical proof. And in volume of a sphere, it's not like a crazy proof. I just got done proving a formula for volume of pyramids, any pyramid, where the base, whatever the base is, it's that area times the height divided by 3. And I looked that up, and that is correct. And at the end of this stream, I'm going to look up what the volume of a sphere is, and I'm going to see if that is indeed correct. And we'll see if we get the right answer, which should be pretty cool. And just also, disclaimer, I have thought about this before. I thought about, while I was at work yesterday, I thought, and I had to like stop myself. I had to stop. No, Billy, don't think. You're going to make this video. You're going to do it live. Do most of the thinking then. But I did think a little bit. So I have actually a plan. And I might adapt the plan, but I think the plan that I thought of while I was at work, unfortunately, it's very strong. So we're going to go through with that plan. There's probably multiple variations of how you could go about proving the volume of a sphere. But I'm going to use calculus, I'm going to use some geometry, I'm going to use some algebra. We're going to use all of these tools from all of these areas of math to prove this formula. What just happened? Oh, it just got dimmer. Is that all right? What happened? Is there like a cloud? We're using natural lighting. Bear with it. I don't know what to do about that. There's like nothing I can do about that. I mean, worst case scenario, hold on, is this, I don't know. What do you guys think? Oh boy. I'd say this is good. This lighting, right, it's fine. Oh, hold on. What about that lighting? Oh, that lighting's too bright. No, we actually want the other one. I like natural lighting, but it's dark. I think this will do, right? Yeah, this will do. Okay, so volume of a sphere. We know, what do we know? We know a sphere, the distance between the center of a sphere and the edge is constant. You can move that radius stick anywhere along the sphere. It is constant. It is similar in a circle in that regards, but obviously in a three-dimensional sense, right, where it's just constant. with that, we can know some things. We know that if you split a sphere perfectly in half, we know that that's going to form a circle, and the radius of that circle is going to equal the radius of that sphere. Okay? All right, that's pretty cool. All right, so we have this idea already of a circle that is formed from the sphere being split in half. And this right here is R. That's the radius, is the center. And so from here, we've got this split sphere. Okay? Actually imagine in your heads we didn't really cut the sphere in half. We have like X-ray vision, or like free cam mode in like a video game, and so the sphere's whole, it's like a whole sphere, and we've just gone inside the sphere. We're looking, the sphere's like here, and we like poked our heads in, and we're looking around, and we see this, the halfway point, so to speak, getting the sphere. We see this is the circle we get from looking at the sphere at exactly one radius inward, so to speak. Okay, and from this, what do we also know, right? So actually, let me talk a little bit about the idea I had while I was at work. My idea was pretty simple. Oops, I meant to draw that halfway. Oh, bear with the drawing. My idea was pretty simple. My idea was that from going from left to right, we get the cross-sectional area of the sphere from one point of the sphere to the exact opposite point. Obviously, it's a sphere, it doesn't matter, right? It's highly symmetrical, so you can turn it all about. What matters is it's one end of the sphere and to the exact opposite end. All right. Now this is different. This is not the cross-sectional area is not the area you get when you like split the sphere perfectly half. It is, yes, that is a cross-section of the sphere, but it can be different. That's what I meant to say. It can be different. So obviously, once we get to the halfway point, then indeed the cross-sectional area is going to be like, so once we get to here, if you could just imagine the sphere like this, like a sphere, the cross-sectional area will be a circle, right? I don't know if you guys can, it'll be this circle, like kind of, but like turned 90 degrees. Does that make sense? I hope that makes sense. I hope you guys can imagine what I'm seeing in my head, right? So from that, of course, but imagine this. Imagine if we look not in the center, we look over here, or over here, along this we'll call one end to another, we'll call that something so I can reference it to you. We'll call that HD, or horizontal diameter, right? So we're picking a lane, we're picking an axis where it doesn't really, obviously none of this, it's a sphere, right? Turning it does nothing. So we're saying, we're just picking something, we're calling that the horizontal diameter, right? Just so I can reference this length and you guys can kind of get it. Once we're at this point in the horizontal diameter, look at this. All of a sudden, if you could imagine, oops, I didn't draw this. I didn't draw it the best, but all of a sudden, the cross-section of the sphere, it's like if you only split just a little bit off the top, and then you looked at the circle. It's a smaller circle than if you split it halfway. And same thing for over here. This is just a tiny split. You just split like the little top of a sphere. And you look at that circle, the cross-sectional area is very tiny. But it gets bigger as you go to the halfway point, and then it starts to get smaller and smaller again, right until you get to the end. So from HD equals 0 to we're gonna also say there'll be two different HDs. Okay, there's going to be HDV. This is HD as a variable. Okay, so this is our 0 point right here. This is 0. So at this point, HDV equals 0, and at this point, HDV equals just HD, meaning it's full amount, right? It's, yeah, that's my thought process here, okay? Actually, how about this? No. I already established this. We're going to be consistent with it. That'll probably be the least confusing for anyone watching, right? So, now the plan here is, the idea is, the cross-sectional area, right, whatever it is the instantaneous rate of the change in volume. That is the idea. It's not the case for every three-dimensional object, but it is the case for prisms. Prisms is very easy to see. That's clearly the case. Pyramids, it is always the case. And spheres is another one where it is always the case. Well, actually, it is always the case, isn't it? It's not always something you can easily do. Let me rephrase that. It is indeed, in a three-dimensional object, when you establish some sort of dimensional value that will be a variable, all right, and we're trying to find the volume of this three-dimensional object. You're looking at the cross-sectional area with respect to the variable, then that cross-sectional area will be the instantaneous rate of change to respect also to this, the variable, okay? This is like calculus. This is a little advanced. Bear with me, okay? In calculus, there's a very common idea. That's how we know the area, when you're trying to get the area underneath the curve in calculus, what do? You take its antiderivative. You take its antiderivative because you know that f of x, meaning the function, is in and of itself the instantaneous rate of change in area underneath the curve, right? So really quickly, if I just draw this parabola here, so when f of x is this value, well, if you keep going, what do you get? You get a constant rate. Rate of change in the area, right? But of course, it's changing. The y value isn't constant. It keeps growing and growing and growing, with a rate attached to it, nonetheless. With the rate at which it's changing, the growth is changing, right? It's not like a constant, like, oh, it's 2. No, it's indeed, if it's x squared, it's going to be 2x. So we know that f of x at any point is the instantaneous rate, which means that f of x must be the derivative of some formula that tells us the area underneath the curve. That's the idea. It's complex, all right? It's a complex idea, but in essence, that's why the antiderivative, if you ever wondered, any calculus people out there, if you ever wondered, why does the antiderivative give you the area underneath the curve? That feels so random. It feels fantastical, feels amazing, but it's confusing. Antiderivative, what? I mean, the opposite of what we do to get the instantaneous slope gives us a formula for the area underneath the curve? Yes, it does. And that's why. If I can't fully explain it, maybe I'll certainly do a video on that later in time. But for now, we're focusing on this, okay? So here's my idea. If we have ourselves a sphere, and we'll call its radius just r, okay? And if we can figure out what the cross-sectional area is with respect to HDV, then we can integrate from HDV equals 0 to HdV equals HD. And that will give us the formula for the volume of a sphere. Obviously, we're going to probably make HD, we know, is going to equal 2R. I'm just going to put that here. HD equals 2R. I imagine we're going to replace some variables in the end of this, right? So we're going to be left with HD, but in reality, we're actually going to take that out and replace it with 2R, right? So that's just some predicting, right? Not even foreshadowing. I haven't done this before, but I can't imagine anything else. We want a formula that is based in R, not the diameter, right? Or not some weird name of diameter, a horizontal diameter. That's just the diameter, but it's a diameter, in a way where when I communicate to you, you think of something. You think of this. That's why I called it that. Okay? So, now what is the cross-sectional area of a sphere? How do we, with respect to some sort of axes, right? The HDV, right? Well, let's think. When we look at the sphere and we're going from left to right, we see this circle grow and grow and grow, and then after the halfway point, it shrinks and shrinks and shrinks to 0, okay? Well, that's interesting. I've got an idea. We've got, we're gonna formulate a function, okay? Now, let me think. Hold on. Yes, okay. This function, obviously we know, okay, sorry, let me backtrack a little bit. See, this is how you prove things, right? You're trying to create some imaginative way to figure something out, so to speak. All right, so we know the formula for area of a circle is pi r squared. So if we know the radius of the circle, then we can figure out the area, naturally, of course. And so if we can know the radius of the circle of a cross section of the sphere, which is a circle, if we can figure out that radius, we can figure out the area of that circle, of that the cross-sectional area, I like to call it. I like to call that the cross-sectional area, okay? And so we're going to create a formula that can give us this precious cross-sectional area. Let's do it, okay? So we know that looking at this, if we plot this like on a graph, right, this circle. Remember, this is not a unit circle. This is a R circle. The radius is R. It's variable. We don't want to. You want to keep things in variables, right? You don't want to like pick a number. You could probably make it work. Funny enough, if it's a unit circle, right? You can just if you do some thinking, you could realize, oh, instead of 1, it could be any radius value. But anyway, we're gonna keep it as R. Okay. We know the formula for area. We know the function, not a function. You know how to graph a circle, right? It's, you've seen 1 equals y squared plus x squared, or it's radius squared equals y squared plus x squared. If the radius is 1, like in a unit circle, 1 squared is just 1, and so 1 equals, y squared plus x squared. Right. Now, so r, by the way, very important, it is the radius of the sphere. R is not a variable. X and y, those are variables. R is not a variable. Not yet. It will be a variable later, but for now it's not. You understand? You get that, right? Yeah, you guys understand, right? Okay, so what we want to know is what is the y value. The y value will give us the radius of the cross-sectional circle. that the shape when we cut that sphere and we look at it at different points along its diameter, right? We cut it and we see this circle. The radius of that circle we can say is equal to y from this point of view. This is so, when I give that analogy of cutting, I'm looking this way. Okay, I'm looking this way, and we're cutting from here to there. Okay, so you see what I'm saying? I hope you guys can kind of, at least if you can bear with me a little bit. Maybe you can see later on where this leads to. I'm hoping. Okay, so we're going to rearrange this equation, right? I'm going to draw an arrow, right? We're going to say that we're going to subtract. Oh no, I got a better idea. Hold on. Actually, I got a better idea. Because I need to think in terms of space, right? We want to conserve space as much as possible. Y squared plus x squared. Shoot. Bear with me, it's too close to HDV. Okay, r squared, one more time, equals y squared plus x squared. We're going to subtract x squared from both sides of the equal sign, and this will give us r squared minus x squared equals y squared. And obviously we're gonna then take the square root of both sides, and that's just going to give us y equals the square root of r squared minus x squared. Okay, so y, as we established, is equal to the radius of that cross-sectional circle of the sphere. So now, to figure out what is the formula for area of a circle. What is that formula? That formula is pi r squared. So if we want a formula that can calculate the area of the cross-section of the sphere, the circle we get when we cut the sphere at any point along its diameter, okay, then we're going to have to square this value and multiply it times pi. So that is what we're going to do now. And we're going to say, we're going to call it something. Cross-sectional area. We're going to call it CA, and then in parentheses, CA with respect. With respect. What are we going to respect? To HV. Because obviously it depends along here. The HDV will affect what the cross-sectional area is, okay? So we're going to say that CA, now I'm just going to, okay. So I did a little bit of I'm going to have to explain myself just a little bit right now, okay? And let me think also. I see now. I see what must be done, I think. Because in this form, this r squared equals y squared plus x squared, and in this form, now, if you don't plus or minus, by the way, if you just do the regular square root, you're just going to get an actual function, which is the semicircle, right? You're going to get the positive value, right? That's fine. We just want the radius, okay? We're just using it to get the radius. It doesn't matter, this or this, that's both the radius, so we don't really care. We don't care, okay? So, but one of the things with this is that in this form, you place the center of the circle at 0, 0. Right? So the center is when y equals 0 and x equals 0. We actually want not the center to be x equals 0. We want the left side of the circle here to equal 0. So we actually have to move everything right by 1. Okay? So this will be 0, this point will be 1, and this point will be 2. No. Not necessarily. I'm so sorry. Not necessarily 0, 1, and 2, because obviously we're not. That'd be like on a unit circle, right? Let me think. See, this is now you're getting into the technical aspects of math. You got to think of what we need to do to make sure we're doing the math correctly, and make sure we're gonna set ourselves up for success. You don't want to do a bunch of math and it turns out, oh, I messed up at some point beforehand, and now it's all it's no good. You don't want to do that. You want to avoid that. So the way you avoid that is by going through this process of kind of planning it out, thinking. I haven't done this before, so I've got my work cut out for me a little bit here. Let me think. I see. Okay. Exactly here. I understand it now. We, of course, don't want to label this in terms of 0, 1, and 2. We want to label this in terms of 0, R, and 2R. Remember, HD equals 2R? That is how we want to label it here. The idea being, if X equals R, then when R squared minus, that's going to be then the same thing as R squared minus R squared, which is 0. Square root is 0, 0. That would mean Y equals 0, but we don't want that, right? It's basically saying, if this is our 0 point, that when X equals R, it's thinking that this is 1R, so to speak. And that makes sense. The Y, this is Y equals 1. At X equals R, Y would be 0. That makes sense. That makes perfect sense. So we indeed have to actually move this over. We have to move this over to the right. And the way we move things over to the right is we put in parentheses X minus 1, right? Or so I remember. And yes, that should do the trick. So we're actually not done yet. All right, we've got this idea, but of course we got to make a jive with our thinking of, from beginning to end, 0 to some end, short 2R. Right. So what we're going to do is we are going, follow me here, Y equals the square root of R squared minus X minus 1 squared. Okay? And that is going to equal... Do I want to keep it like that? Yeah, for now I'll keep it like that. So yeah. I don't really see too much of kind of why you wouldn't keep it like that. Why you would kind of complicate it. I feel like if you were to try to mess. Yeah, that'll be fine. We'll keep it like this. It's fine. All right. So now this is actually representative of what our model is, right? We have this model. We've created an equation. Now the y really does equal this. The y is going to be, we want the y, for instance, to be r when x equals r, okay? And it's a little hard to see here, r minus 1, in parentheses, squared. Really quickly, let me check that. Yeah, so it'd be, r squared minus, that would be the same thing as just 2x of 2r plus 1. Hold on. I'm just going to really quickly do it out here. I'm just kind of curious here. I'm a little nervous too. Minus. So obviously we're going to have parentheses x squared minus 2x plus 1, close parentheses. And we're inputting my nephews are here. That's all good. Hey guys.
Hey.
Yeah?
Okay, we're downstairs.
Hold on.
I don't know if you were.
Yeah, I'm still streaming, but don't worry. I'll be done hopefully soon enough. Oh my gosh. It is hot in my room. Close the door. I'm cut off from all air conditioning here. Oh my gosh. Okay. So what are we trying to do now? Oh my god. I know why this is all wrong. I can't help myself, guys. I can't help myself. You guys were probably blurting it out. Billy, what's wrong with you? You just said we're not trying to use a unit circle. I know. I can't help myself. I just did a video. I'm editing it right now with Danger Dan. And it was on the unit circle. So my brain is still there, okay? -1. What if the radius doesn't equal 1? Did you think of that, Billy? Did you think of our model? Oh, God. Okay. Yeah, guys. Okay. There's another thing that happens when you do something, off the cuff, live. You make little mistakes like this. It's obviously -r squared. We don't want to move it over by 1. What if the radius doesn't equal 1? Jeez. No, we want to move it over by r amount, right? Whatever r is. It'll be perfect every time. All right. So r, if the radius isn't 1, it's not gonna mess everything up, right? That's the idea. That is our big idea here. Okay. Now this makes a lot more sense. Now, if you do it out, when x equals r, you're gonna get an actual good answer really quickly. Let's just quickly see this. We're gonna have r squared minus. I'm factoring in the negative. By the way, so that's gonna be plus 2x r minus r squared. Okay. Now, see, this is actually a valuable lesson here. Really quick, I just want to make sure I did this correctly. Yeah, I did this correctly. Yeah, plus you factor in the negative. Absolutely. There's no questions about that. Right? Yeah, it's plus, there's 2 of them, so it's 2xr. It was minus 2xr, but now, because we factored it in, it's plus. There's no doubt about that. Yeah, and then when x equals r squared, that's going to be negative r squared plus 2, remember, this is going to be 2r squared. All right, what's 2 of something minus 1 of itself? That's just the other half, so 1. It's going to be 1r squared, square root of that. Square root of r squared is just r. We get the right answer here, right? So you don't really have to test this if you make sure to not make a mistake. I have to do this because I'm a human being. Okay, because I'm human, I have to run these tests because I know I don't have a perfect mind. Because of my flawed mind, I can come up with all sorts of stupid things to say and to think and to write down. So this is why if you're a human being, you have to test your math. You have to, with math. Make Make sure we make that clear. You do not ever, ever test math using like physical experiments, okay? That the huge no-no. All right, that's science. Science uses the physical world like measuring. In math, we never measure. We never measure anything. Never, ever, forever, okay? So we don't measure angles, including, I know, like, oh, but what, how do you know if you have a 90, you know if you have a 90-degree angle. You can just draw it, okay? You know if you have a 40, you can, and if you're off by a little bit, what I love to do in my notes, I do this all the time, I say pretend. Pretend it's what I say it is. If my drawing looks off, pretend it's perfect. Excellent. Excellent. That way, I don't need a straight edge, I don't need a protractor, I don't need any measuring device or even a straight edge. Oh, but that's just to make your drawing look better. I could be convinced if you want to have nice drawings, okay, you can straight edge, maybe. But no, because then you can make that same argument for a protractor, and I don't believe in protractors. I think they're dumb, in terms of math, of course. Yeah, throw out your protractors, throw out your rulers, your straight edges, just throw all of it out. A compass, you don't need a compass. I drew this circle. You guys know it's a circle because I say it is. Is it actually a circle? Absolutely not. This is not an even circle by any means. Look at it! The R on this side visually looks different than the R on that side. They're supposed to be the same. I don't care because that doesn't matter to me. What matters is I'm pretending it's a perfect circle. In my brain, it's a perfect circle. Okay? Math-wise, it's a perfect circle. That's the idea. And by the way, we absolutely wanted to factor this out because I noticed that way earlier. Don't get me wrong. It's not like I'm not that dumb. Right? Like I don't notice an opportunity to simplify. I noticed it, but I just was going to do it later. You guys understand. Okay. So we get y, we're going to go back in this, y equals the square root of, I'm going to actually rearrange this, 2xr minus x squared. So instead of negative x squared plus 2xr, it's just 2xr minus x squared. So now the formula for the cross-sectional area, right, we have to square this and then multiply it times pi. This squared is just going to cancel out with the square root. So C cross-sectional area of, I know I was going to say HDV, but people, listen here. I changed my mind. HDV, that's 2 letters and then a small V. And like bottom right corner. No. Dumb, right? Am I right? You guys can see the math, right? Okay, yeah. You guys can see the math, right? You guys can see? I hope you guys can see. Hold on. I'm paranoid now. Oh, yeah. Oh, that's a better look, right? Oh, gosh. Okay. I'm going to write a little bit bigger from now on. Oh, gosh. Now I have to be like this. Oh, this is weird. Hold on. I gotta move it. Sorry, guys. I gotta move it a little bit further back. Technical difficulties? Why can't... I'm too stupid to angle this camera good. Okay. Yeah, you guys can read that, right? There's no one watching. There's no one watching this. You'll be fine. I hope you guys can read this. I have to stand here. It feels weird standing here. It feels like I'm blocking it, but I'm not. I can see that I'm not blocking it. Okay, so I changed my mind. Instead of HDV as our thing, we are going to use we're going to use X. Why not? Why not? We have X equals 0, X equals R, X equals 2R. Seems good to me. Seems good to me. We're going to use X instead of HDV. I get it, HDV earlier, because I'm thinking it's like the HD, but like as a variable. The HD is like a set. You can't change it. Not now, at least. But then the HDV is like the variable version, right? But, you know, I'm changing my mind and I'm saying x is the variable version of HD. Yeah, and you guys will have to take it. Because that is what I feel like doing. Because x is probably nicer than 3 letters, I imagine. So, oh god, I gotta stand like super close. My god, this does not feel natural, but I'm doing it for you. Okay. CA of x equals pi parentheses. You guys can see, right? Okay. 2xr minus x squared, close parentheses. Excellent. Oh gosh. Hold on. Let me see. Yeah, you guys can see that. Hold on. Can I see this? Yeah. Okay. Sorry about that. Alright. We're going to go over here now. Okay. Well, we want to know. Should we factor the pi in? Really, I'm so sorry. Factor pi, yay or nay? Do we want to factor in that pi? Man, oh man. What do you guys think? Yay or nay? We don't need to factor in that pi. Screw the pi. I don't know. We're factoring in the pi. We actually have to. Yeah. All right. So now we're going here. Okay. I'm writing in big letters this time. We're going to say I'll rewrite this. CA of x equals oopsie daisy. Hold on. 2 pi r x. I'm gonna write a little dot between the r and the x. That way you know they're not together. Minus x squared. Okay. Minus pi x squared. Whoopsie daisy. Minus pi x squared. Excellent. Much better. Okay. Now, what we're going to do is we're going to integrate this from x equals 0 to x equals 2r. And that will get us the volume of the sphere. Okay? Now, let's commence, right? Let me think. Yeah, this will work. I'm sure this will work out in the end. If I've done something wrong, if it doesn't look right, I'm just going to look back to see what I did wrong. I mean, whatever answer I get, we'll just check it. I might get it wrong, and then, you just got to make sure you do it right. No. When we get our answer, I'm just going to really quickly double check to make sure I did everything right before looking at the computer, looking at the internet. So, we're going to integrate this. So, from here, we're going to have our integral, and it's from 0 to 2r. 2 pi r times x minus pi x squared. Yep. And do you put parentheses? Yeah, you don't do that. It doesn't matter. Dx. Okay? And now we have to integrate. This is lovely because this is just the power rule, reverse power rule. All right? The power rule of antiderivatives. All right? So 2 pi r x. Obviously, because of that minus sign, we do it in these two batches. They're two separate batches. We can treat them, the integral of this whole thing equals the integral of this because the integral of this. That's a rule. You don't know. Same thing with derivatives. So, antiderivatives, derivatives, same rule. There. Okay. So 2 pi r x. How do we do that? You're probably freaking out. Oh my god. Look at all those variables. Oh my god. Are we going to have to, is this multiplication, we're going to have to use like some sort of fancy integration technique? No. Because with respect to x, r does not change. With respect to x, pi certainly doesn't change. And with respect to x, 2 does not change. Okay? Remember, we're saying the y here is the r of the circle that is the cross-section of the sphere. That's different. That's different than the r in the sense we have here. The r in the sense we have here is like doesn't change where depending on where we are, the cross section. It's like a constant. Right now we're treating it as a constant. We're treating it as like, oh, the sphere is 2r wide. The diameter is 2r. The radius is r. You see what I mean? So that's not the same, if that makes sense. All right. It doesn't change with respect to x. This point right here doesn't change with respect to x. X might equal r, it might not. You understand? So that is why we can treat this as a simple power rule thing. This is just a constant. So what this is going to equal, if I remember this correctly, we'll use parentheses because I don't know if you use something here. I don't know what the technical rules are. What's the antiderivative of x? That's just going to be x squared over 2. That 2, I'll write it. Whatever, I'll write it. 2 pi r times x squared over 2. And by the way, if you don't know, obviously, this is the same thing as if it was all over 2. Because nothing's getting added in this section here. So you can cancel out. All right. Some people get confused. I've noticed, like they think, oh, but the order and division matters. But yeah, that's it. It matters in what's divided by what. It doesn't matter. You can put the 2 over the r, over the pi, over everything, over some of it. It's the same thing. It's like multiplying by 1/2. It doesn't matter which one you multiply by 1/2. Multiplication has a property. Right. Okay, I'm like explaining every basic math principle in this video. I don't need to do that, right? I do not need to do this, okay? And we're going to subtract, same thing with here. What's the antiderivative of x squared? That's just going to be x cubed over 3. So we're going to get pi x cubed over 3. Excellent. And then the way I remember it, you have like a bar. You have this line, and it's from 0 to 2r. And that then equals stuff, so to speak. We have space. Yes. Oh, no. That arrow is way too long. There's no reason to take up that much space. Okay. So now, behold, we're going to fill in, as per the rules, right? It's the final minus the initial. So the final is 2r. We fill in 2r for x. Okay. Put it out, and then we're going to do that whole thing subtracted by if r was... if x was 0. Spoilers alert, that's going to be 0. And then we go from there. Okay. Yeah. I feel like I've made a mistake. We'll figure that stuff out later. If I made a mistake, we'll figure that out. We'll have to... Yeah. No. I don't know if I did. We'll see. If we did, we did. It's fine. Okay. So now, what do we do here? Yeah. So we're going to have, pi r cubed, right? Because x equals 2r. Oops. 2 squared is 4, so times 4. I wrote a dot. I didn't need to write a dot. Oh, well. They're over divided by nothing. Yeah, that's right. Yeah, because it's just that. Yeah. Okay, that's done. I'm getting nervous now. I don't know why. I think it's all going to work out. And then cubed 2 to the third power, that's 8. So we're going to have minus pi times 8. Honestly, you want to put like the numbers in the very front. Whatever. Doesn't matter. Doesn't matter. It's people do that just for whatever. Over 3. So now, yeah, that looks good. You guys can. Oh shoot! I probably am like out of the camera a lot of times. You guys at least can see the math, which is good. Okay, so now what do we have here? Our denominators are not the same, so we can't combine these yet. Okay, we know that. So we're gonna have to multiply the top and bottom on this side by 3 to make this a thing we can do. Makes sense, right? So multiply the top and bottom by 3. How do I want to do this? Because our arrow's in the way. Darn it. See? This is why. There we go. So you see, and this means continuation. Just arrows. That's what that means. Okay. So multiply this by 3. Damn it, I meant to draw a parentheses. Oh, darn. No! It's all falling apart. No. Okay. Saved. 3 and 3. Alright? Now we can, and you didn't need that parentheses. It's all multiplication. Billy, think. Okay. Okay. Whatever. Okay. We have 3 times 4. That's going to equal 12. Okay? So right now we have, we'll just write it out here. We'll have 12 pi r cubed minus 8 pi r cubed all over 3. This all over 3, again, I know, Billy, with the math lessons, I'm trying to go back to the beginning of time. When you're making a math video, you can't just always go back to the beginning of time. It's dumb. It's like, because then I'm going to, logically, by that extent, I should teach you how to add and subtract and multiply. Okay, but because that minus is there, it's all over 3. Whatever. Okay, 12 minus, so we notice all these things are the same. It's 12 of something minus 8 of the same something. That's just going to be, in the end, 12 minus 8 is going to be 4 of that something, right? So that equals 4 pi r cubed all over 3. Oh. Is that the answer? And I believe this is the answer. I ain't circling it yet. No, I'm going to walk over to my computer, I'm going to Google this, and I'm going to know if I got the right answer. Hold on. Volume of a sphere. 4/3 pi r squared. Yes! Hold on. Victory. Checkmate. If you guys watch Atun Shea Films, that's funny. He has this thing called Checkmate Lincolnites. Very good YouTube channel. Recommended. Follow Danger Dan 19. Follow Atun Shea Films. Alright, he has this hilarious series on YouTube called Checkmate Lincolnites. It's hilarious. It's worth it. Alright, but I feel like that guy right now. Oh yes, Checkmate Lincolnites. Yeah, no. But instead of that, which is that's a caricature of it's a joke. But here it's like this is also a joke, but it'd be I don't know. Was there anyone who thought I couldn't do this? Oh, we can circle it now. Now, Google had 4/3 pi r squared. That's the exact same thing as what I have here. If anyone makes a fuss about that, they just don't know math, basically, Same thing with the trapezoid video. I actually Googled it later. Google changed their answer. Google likes to have things now in A, B, and C. I think that's where math is going. So back in the day when I Googled it to figure out, when I did the proof for the first time, area of a trapezoid by myself, I Googled to see if I had the right answer, and they use B1 and B2 as like the base, the top and bottom of the trapezoid, so to speak, top and bottom, right? And it's base 1 and base 2, that's what that stands for, that makes sense, times the height. In Google, they use A and B as base 1 and base 2, and then they use C as the height. That's kind of interesting. I don't know how I feel about that. I think it actually is good. Honestly, I think maybe that's where I should go to, where you use A, B, and C, you just go down the alphabet for like all variables, and then you just explain what those are. What is A in this page of math, in this chapter? A might be in the Pythagorean theorem, and then it might be a thing in a trapezoid. So it's a different thing, and you just explain that. You communicate the fact that it's different. Anyway, I think it's time to end this stream. My nephews are here. They want to play video games with me. They want to chill with me. They want to hang out. We're going to have a fun time. So, and a video is indeed coming soon. Spoiler alert. With the video, not really spoiler, announcement, video, we're going to have a video posted on my channel sometime in the future. I don't know exactly when. On the unit circle. That'll be very fun. Unit circle is very, very fun. Very awesome. Okay? Any questions? Leave it in the comments. I really hope I don't fuck this up. I'm going to save this video. I said it. There's an option. I'm like, save video. Yes. I think I clicked on it, which is good. We're going to save this live stream. Questions, you just post those suckers in the comments, or in the comments of even other videos. You can, this has a comment, right? Okay, yeah. Danger Dan, is that you? Better? Oh, shoot! Oh, I have one viewer! I think, were you here this entire time? Can you say something? Say something. Oh, he might have left. The one might be me. I think I said 2 earlier. Oh, that makes sense. Okay. But anyway, that is the end of the video. That is indeed, when we say that is the volume of a sphere based off its radius. Radius being r. Okay. We did it. I did it for the first time. I did it live. I think that's pretty cool. You guys, hopefully I wasn't too crazy and you guys could see, you could peek into what the process of doing a math proof. We used algebra, right? The idea of graphing, and calculus is kind of, calculus, if you don't know, it's very much an extension of algebra. It's all about functions, right? Calculus is built upon functions and graphs, and so is algebra, at least, like algebra 2 kind of algebra. Anyway, we also use geometry, the idea of knowing the properties, the definitions. It's more the definitions. What's the definition of a sphere? That is really key, because we had to, using our definitions, using the rules, we were able to do this proof, okay? Because we were consistent with the rules. And yeah, and we used like basically 3 different maths, or if you want to lump algebra and calculus in the same group, whatever. So 2 or 3 different maths, and we got our answer here. Okay, math is very interconnected, if you didn't know that. All right, I'm ending the stream. Bye, everyone. Oh, it's super bright. Okay, bye.